So the next talk is Safe Power with PMD Threads, Load-Based Sleeping by Kevin Trainer from Red Hat. So go ahead and take it away.
About how to save power with PMD thread load-based sleeping in OVS DPDK. Okay, so what we look at is we look at OVS user space PMD threads. We look at some things we need to do for system configuration. We look at some options we have for doing less work in OVS user space PMD threads. We'll talk about some tuning that can be done. We'll look at the PMD load-based sleeping operation, how it actually works, and then we'll do some testing. Right, so an OVS DPDK PMD thread, it usually runs one-to-one isolated on a core, so nothing else is running there. It does the data path processing, and the two things that it mainly does is it pulls the RX queues, so it runs in a loop in user space and it pulls all the DPDK NIC ports and the vhost ports for packets. And if it finds some packets there, it processes those packets. So it does things like classification, whatever actions need to be done, and then usually it ends up outputting those packets to a port. So this is typical of behavior of a type of DPDK application in a run to completion model. So the characteristics would be a high throughput, a low latency, and a high CPU cycle usage. So the question then is that high CPU cycle usage a bad thing? Well, if those cycles are being used efficiently to get that high throughput and that low latency, then I'd say the answer is no. But if those high cycles are being used and we're not getting packets or we're not doing work, then maybe the answer is yes. Right, so if we did less work, would we actually save, would that translate to some saving some power? Well, we have to look at the system for this. So we usually have the PMD thread cores, the cores that those threads run on, isolated from the system. So hopefully there should be nothing else using them. And we also need to enable C states for those cores. So C states are the processor operating states. So we go from C0, which is full power, all the way down to C6, which is the deep sleep state. And we can enable them on the BIOS level, so we need to make sure that's done. There's a little snippet from my BIOS. We also need to make sure that any system tuning software, such as TuneD, allows the processors to go into that deep sleep. So we have the CPU partitioning power save profile in TuneD that was added not too long ago in TuneD 2.20, and that allows the typical kind of CPU partitioning profile things, but it also allows the cores to go into a low power state. Another thing we need to consider is, what about the other cores? So we have maybe 28 cores in a socket. We have 2 for the operating system. We have 4 we're using for the PMD threads. Well, there's 22 other cores, so what are they doing? So that might be a factor as well. Okay, so how are we going to do less work here? So there's a couple of options. We have sleeping and we have nappy. So if we compare them, we have sleeping, we sleep between poles. So as we loop around an OVS DPDK user space, doing the RX on the ports, we just insert some sleeps. For nappy, we'll change the device into an interrupt mode. The sleeping is agnostic to any device type because it just runs in OVS DPDK user space. Whereas the nappy, each device driver is required to support interrupt mode in order for that scheme to work. And that's not mandatory in DPDK, although I guess most of the NICs would support that at the moment. Sleeping would be a very simple implementation. As I said, it's just inserting some sleeps in a loop that's already there. Whereas nappy would be more complex because different types of devices would need different type of code in OVS to put them into interrupt mode. So for example, DPDK NICs use the DPDK ETDEV API, and they would have one set of calls to put them into interrupt mode, whereas the vhost ports that we use for talking to the guest use the DPDK vhost library API, so they would have a different set of code to try and put them into interrupt mode. And that's of course dependent on all those devices supporting it. So for sleeping, one thing to note is that if there's absolutely no traffic, then there would be still some wake-ups because we don't want to sleep forever. So we'll sleep for a certain amount of time and then we'll wake up and we'll poll and we'll go back to sleep again if there's no traffic. Whereas nappy, it doesn't wake up when there's no traffic. So that would be an advantage to nappy. Sleeping is gradual and adaptive to the packet rate. So we can put in a lot of sleep, like big sleeps, or we can put in small sleeps. And we can kind of start with a very small sleep and we can gradually grow it and to see where the steady state for that traffic rate is. And maybe we can insert some sleeps even when there is traffic running. Whereas nappy is binary, whether the device is either in interrupt mode or it's polling. So it makes it more difficult about the threshold of where you switch over between interrupt and polling. So there might be cases during those transitions or those low traffic rates where it's not as easy to decide whether nappy should be in interrupt mode or polling mode. Okay, so and this presentation is about sleeping. So how long should we sleep for? Well, when you think about what happens if a packet arrives during a sleep, what happens is it must wait until after the sleep before it's processed. So there's a trade-off here between longer sleeps and a greater wake-up packet latency. So if we sleep longer, we'll do less work when there's no packets, which implies more power saving, but we have a longer wake-up packet latency. So those first packets that come back when there's a sudden traffic burst might have to wait a little bit longer because the sleep has to finish. Whereas if we sleep shorter, we do more work when there's no packets, which implies less power saving, but there's a shorter wake-up packet latency. Okay, and we can tune this from the command line. So we've seen here with PMD sleep max equals 100, sets it to 100 microseconds. So that means the maximum amount that we'll sleep is for 100 microseconds before we poll again. Okay, we also need to consider the processor C-state wake-up times. So I've shown them on the little caption there from my system. So, and you can get them with CPU power command or just by looking in the directory. Okay, so let's have a look at how the PMD load-based sleeping works with a low traffic rate. Okay, so let's say we set PMD sleep max to 50. So the maximum amount of time we're going to sleep for is 50. Well, the PMD thread will poll an RX queue. It might get 32 packets this time, just to show this. It'll process those packets. As it got 32 packets, which is the batch size it looks for, there's no sleep because we're receiving packets. So why would we want to go to sleep? We have work to do. Then we'll poll again, poll the RX queue on the second line. We'll get 2 packets. We process them. But we got a very low amount of packets, so maybe we can start to do a small bit of sleeping and not poll as quickly. So we sleep for a microsecond. We poll the RX queue again. We get 0 packets. Okay, let's increase the sleep because there's nothing to indicate that we need to poll it faster. Okay, so this is where we're transitioning to the max sleep time. And let's say this kind of pattern continues with where the ... is, and then we get to the steady state where we're getting 5 packets and we're processing and we're sleeping for 50 microseconds. And that's the traffic rate is such that it's 1 packet every 10 microseconds, and we're able to hold that, use our maximum sleep state, use our maximum sleep time, and we can still process all the packets that are coming in. Okay, but then let's say we suddenly at the last line there we get 32 packets, and we have to process them. Well, we want to transition very quickly back out of the sleep state into a full power state, because we don't want, if there's a change in traffic to, and there's a sudden burst of traffic and now the rate is high, to gradually get to a point where we can accommodate those packets. We want to go straight back to full power. Okay, so let's look at the same thing, except if we had 100 microseconds for our PMD sleep max. So again, the first steps would be the exact same. We won't sleep when we get packets. We'll start to sleep when we get a small amount of packets. But in this case, in the steady state, we're getting 10 packets every 100 microseconds. So it's the same traffic rate as we had in the previous slide where we're getting 5 packets every 50 microseconds. But the difference here is we're not polling as much, so we're doing some less work. So in this case, potentially we'd save some more power. And then again, we transition out of the sleep state as quickly as possible. This isn't directly from this test, but we just to show that we also have some information in the added to the PMD perf show command that shows of the iterations, so the loops for polling, how many times did you actually have a sleep, and what's the average of those sleeps. Okay, so let's do some testing next. Right, so this is our test topology. It's a typical kind of PVP test. We have a traffic generator. We have some DPDK NICs. We send traffic in to the DUT. OVS DPDK runs. We have some cores dedicated for the PMD threads, so 836, 10, and 38. We have some vhost ports up to the guest, and test PMD forwards the traffic to the other port. So a normal kind of PVP test. So what do we want to test and what do we want to measure? So we want to measure what would happen with the different traffic rates. So max throughput, and it doesn't matter what that is, but the point about this is when the PMD thread looks for packets from any of the NICs, there will be abundant amount of packets there. So it'll always get 32 packets in the batch because we're sending it faster than, or as fast as the system can handle. We'll try with 1 million packets per second. We'll try with 1,000 packets per second, and we'll try with 0 packets per second. Now we'll also look at different max sleep times because that's an important part of the tuning. So we'll try with 0 all the way up to 500 microseconds for the max sleep time. And all these tests are with 64 byte packets, and they're on rel. So measurements, what do we want to measure? We want to have a look at this, what the C states are of the PMD thread cores. We want to look at the power usage of the socket that they're on. And we'll also do some testing around wake-up latencies. The tools used were PCM power, CPU power, power stat not as much, and power top I didn't use, but it's just handy to just include it in the list. Okay, so let's look at with our max throughput. So this is not a very interesting chart, as you can see. So on the horizontal axis, we have the PMD sleep max time. And on the vertical axis, we have the percentage of time spent in each C state. So we can see that it's in C0 all the time. So why is that? Well, we never sleep because we always have work to do. So it kind of makes sense that we'll never go into a low power state. Every available cycle is used. There's no time for sleeping. Okay, and if we look at the power consumption, as we would expect, we're doing the same work in each of those cases. So we're going to get the same amount of power used, which is in this case 63 watts. Okay. So now we look at the 1 million packet per second case, and we see something a little bit more interesting. So for 0, it means we don't do any sleep. So we see what we saw previously, where we just stay in C0. But for the other cases where we allow some sleeps, we have some, we drop to C1 at certain points in time. So why is the 10 and the 500, why are they all the same from the 10 onwards? And the reason, of course, is because even though we allow a max sleep of maybe 200 or 500, we never actually reach that. We've allowed a max sleep of 10 in the 10 test, and that's probably sufficient in this case because we don't actually get to sleep longer than, or even maybe even up as far as the 10 microseconds. So even though we increase the max sleep to 50 or 100, we never reach there. And similarly, we see that when we start to use C1 from 10 onwards, we drop the power down to 61, and I think the 6061 is probably just a margin of error between 60 point something and 61 point something. But there is a drop of a couple of watts because we're using C1. Okay, so 1000 packets per second. So this is a much more interesting case. So we can see again our baseline with no sleeping. We see it's on C0 with 0 microseconds. With 10 microseconds, we see that we hit a lot of C1, okay, as we did before. But we even hit more C1 this time because the traffic rate is lower, and I guess we can get further up nearer to that maximum, or maybe at that maximum of 10 microsecond sleeps. When we go to 50 microseconds, we start to move to the C1E state. When we move to 100 and 200, we are predominantly in the C3 state. So why would the 100 and 200 look the same? I guess the reason is we're in a state where we can get to the C3 state, but we can't, the threshold for the amount of work the processor is doing to get to C6 hasn't been hit yet. And we can see that in the 500 microsecond case, we start to hit C6 some of the time. Okay, so let's look at the power consumption. So again, 0 sleep max is the baseline case of 63, and we see that there's a good drop in the power used when we allow the different different max sleep times. An interesting thing is that the 200 and the 500 are almost the same, and we'll come back and talk about the 500 a bit later. So now let's look at the 0 packets per second case. Okay, so we've stopped the traffic. There's no traffic at all. Again, we have 0, our baseline case. We see 10, 50, similar to the 1K packets per second case. The 100 and the 200 were predominantly in C3. So why are we in C3 if there's no packets? Because we have a sleep time, so we still wake up the pole, even though we don't get any packets. Then when we move to the 500 microsecond case, we drop down predominantly into the C6 state. Right, so we see something similar to the 1K, a little bit more maybe. We drop down, so from 63 all the way down to 53, 51, 50. So that's quite a big saving. Again, we'll talk about the 500 a little bit later. We don't need to go through this. This is just all the results from the previous graphs or the previous charts put onto one chart here. So we can look at on the horizontal axis the packets per second, and we can see what the power usage is with each of the different PMD sleep max times. Okay, so the wake up packet latency. So we just look at a limited range in this chart because otherwise it's too difficult to see. So an important point to remember is not all packets will be wake up packets. This only applies to the first packets that are coming along after a sleep or during a sleep. And for the testing that I've done here, this is when the max sleep has been reached. Because otherwise, if we put max sleep to 100, but we're only sleeping for 5 microseconds, then we don't really see what could happen. So I've forced the max sleep to happen, and every one of these packets that is sent is a wake up packet. So it's the worst case that can happen, I guess. Another thing we need to consider is that there's an ingress path and an egress path to PVP, and they're using different PMDs. So we actually can hit a sleep in both directions. So we can hit a sleep on a PMD ingress towards the VM and test PMD, and we can hit a sleep in the PMD on the way egress. Okay, so if we take the 0 microsecond case, we can see that's our baseline, and that most of the packets are in the 10 microsecond bin, okay, which is like, I guess, 0 to 9. And then if we move on, we see that as the PMD sleep max increases, so does the latency on the wake up latency on the packets. If packets are going at full throttle through the system, then the latency, there'd be no sleeps, and the latency would be similar to the 0 microsecond case. Another interesting thing to note is that there seems to be a range. So if we take the 50 microsecond case, we can see that there's a range spread out there. And I guess when a packet arrives, the system may be in a certain time into a sleep. So it might be just ready to exit that sleep, in which case the latency would be quite quick for the packet. Or it could be just have gone into a sleep, in which case the packet will have to wait some longer. So we see a range in values. Okay, so I won't cover this slide in the presentation, but it's just there for a reference, and it's just to add the 200 and the 500 microseconds. Okay, but it's a bit hard to see. All right, so 500 microsecond sleep. Is there something suspicious here? So 0 packets per second. If we look at the chart on the left, 0 packets per second, mainly in C6. 1,000 packets per second, C3 and C6 mainly. But then we look at the power on the chart on the right-hand side, 0 packets per second, 50. 1,000 packets per second, 51. Okay, so very close. So why doesn't C6, if we're in C6 for 0 packets per second, why don't we get a bigger power saving than when we're in C3 and C6? That was something that kind of puzzled me a little bit. So what I had to do was look at the device under test and the cores on it as a whole. Because all the tests so far we focused on the PMD cores and only them. I said, okay, we have PMD cores here, which are in one box, and we're also running some cores for the test PMD in another box, highlighted there. Okay, and when things are full power and we've no sleep, PMD threads, I put them as red to indicate that they're busy and they're in use, and test PMD vCPUs that are used for test PMD, they're in use as well. And we were measuring 63 watts, so that was our base case. Then we put in a sleep of 500 microseconds, and let's see what we saw. Okay, so we saw that we reduced, we got into like C6 state on the PMD thread cores, so we're going to mark them as green now to say they're not really being used as much. And the test PMD vCPUs are still being used, and we hit 50 watts. So then it got me thinking about all those other white boxes in the diagram. So what are they doing? So really, what my system looked like was not this; it was like this. So all those cores were doing nothing else, or virtually nothing else. Okay, like I didn't have other VNFs or other test PMDs running. So really, we just had these two cores that were running for test PMD that were doing a lot of work. So I stopped them just to see what would happen. And lo and behold, it dropped a lot of power as well. So I guess the point about that little side note is that the PMD thread cores could be 4 or 6 or 8 for a system, but there's a lot of other cores in that socket that are doing things. So probably, we can definitely save a lot of power. We've shown, I think we went from 63 down to 50. So that's a big saving. But probably, like things like VNFs also doing some power saving can bring the whole system power down even further. Okay, so to summarize, we saw the feature. It's available in OVS 3.2. There's an experimental version in 3.1. There's a trade-off between the max sleep time and the power saving, especially under the kind of 0 and lowest load and for those initial packets. Sleep time will adapt to the traffic rate. We'll transition gradually into longer sleeps, and we'll transition quickly back to full power. We definitely need to consider the configuration of the system. If we don't have C states enabled or our tuning software doesn't allow it, we won't save anything in power, even if we're saving cycles. And other cores matter. So again, this infrastructure for the PMD thread cores is only a small amount. All right, thank you.
All right. All right. Thank you very much, Kevin. I think you're online, so welcome.
Yeah. Hi, guys.
Let's see if there's any questions. I haven't seen any questions yet. Let me just quickly go. So no questions yet. I guess a lot of information to absorb in your presentation, a lot of slides. I think what I understand from the conclusion, waiting for some questions, is that looking at the latency, it really depends on where in the sleep you are, right? So if you set up some new sections, you sort of can determine what the worst case latency is, which is your max sleep, I guess. And then, yes.
Yeah. Well, I suppose there's a couple of things to consider. There's your max sleep, but you also have to consider if it has two paths, like an ingress and an egress. The other thing you need to consider is that if one of those PMD cores, thread cores, has gone into a sleep state like a C3 or something like that, that you could have the additional wake up latency for that as well. And that was something that, like, so sometimes potentially even going into C6, if you saw the if you saw the difference in the latency times between the C6 and C3, I think it was 40 microseconds for C3 to wake up and 133 microseconds for C6. So there could be a balance where at times you actually might be better off for wake up to be in C3 and have that shorter wake up latency. So that's a factor as well.
Okay. Yeah, thanks. Yeah, especially the one that I didn't thought of that you mentioned again, I think now, is that the latency also on the reverse path, right? So if you hit the physical port and then the vhost also coming back to a PMD. Yeah.
Yeah, because that surprised me when I measured it and I went, why am I seeing double what I expect to see?
Yeah.
And then I was like, oh, sure, of course. I was using two different PMDs, so they were both sleeping, and I'd kind of engineered the test to send packets at a low enough rate so that they would hit, the both of those PMD thread cores would be somewhere along in their max sleep.
Okay. Yeah. Nice. Thanks. We do have a couple of questions, so let me run through it. So one question from Mike Patrick is: are these results expected to be stable from CPU to CPU? And I guess he means CPU series, and also from vendor to vendor.
I would say no. So I would say certainly things like the C state wake up times. I think that's something that is a focus for like newer generations of processors to reduce them. At least that's the kind of thing I've heard. So I guess there will definitely be a bit of your mileage may vary. So no, I wouldn't be putting any guarantees on them.
All right, thanks. And then one final question or remark from Aaron. I think he says that it's you've been working on this for quite a while, and it's great to see the results of all these test metrics. And he is asking if you expect that there will be maybe a way in the future to automate the remove of some of the user management part of it.
Yeah. So the only, well, I guess from an OVS perspective, the only thing that needs to be set is the max sleep time. So that could be, I mean, that was kind of deliberately left as PMD sleep max to make it clear kind of about the potential for latency. Because we kind of brainstormed at the time, should we call this a power saving feature? But then if the system isn't right, it won't save power. So we actually tried to call it exactly what it is, sleep time. Yeah, I think there is going to be integration into things like OpenStack, and part of the work, I guess, was to put in the TuneD profiles that was done by some of the OpenStack team. I'm not sure what else. Maybe there's something else you're thinking of that I've not covered. But yeah, from an OVS perspective, it would just be that max sleep time.
All right, cool. And then I think one final question from Flavio. He's asking if there's any documentation to guide the users how to find a trade-off between power saving and the latency when using this max sleep?
Yeah, that's a good question. I'm not sure if there's a guide. So there is a blog that I should have put a link in the slides. I just have it here. There's a blog that, I mean, I guess the presentation now as well, maybe will kind of at least spark the ideas to think about it. But yeah, there isn't a guide as such. I guess it will be, users would need to test it, but in particular, they'd need to think about what's the max latency that they're comfortable with. So, it may be high, it may be low, and that needs to be kind of, I guess, the focus of what they want to test, and also as Mike said about what CPU they're on. So I'll just put a link to the blog in the chat. These were a different set of tests I did, but they're kind of similar. It's abbreviated a bit. There's no it doesn't have the C state stuff in it, because I was like, at the end of the day, you could tell me I'm in C0 or C6 or C100. All I want to really know is how much the power has gone down. But I guess for the focus of the presentation, it was worth looking at.
All right. Yeah, thanks for sharing it as well.